Rub a piece of amber against wool and something impossible happens. The yellow resin, fossilized tree sap, hardened over 40 million years, begins to pull. Feathers lift toward it. Dust, straw, and threads of lint jump across the gap and cling. The ancient Greeks noticed this near 600 BC, and Thales of Miletus puzzled over it, but no one could say what the force was. They had a word for the amber itself, electron. They had no word for the pull. For 2,000 years it stayed a party trick, a curiosity with no name and no explanation, a whisper of something invisible that no philosopher could grasp. Then, in the year 1600, an English physician named William Gilbert changed everything. Personal doctor to Queen Elizabeth I, Gilbert spent 17 years testing, not just theorizing. He rubbed amber. He rubbed glass, sulfur, sealing wax, and gemstones. He built a tiny pivoting needle he called a versorium, the first electrical instrument, and watched it swing toward every charged body he brought near. Object after object, he recorded which ones pulled and which stayed dead. Gilbert realized the amber effect was not unique to amber. It was a shared property, a force that many materials could hold. In his great book De Magnete, he separated it cleanly from magnetism, which he studied by carving lodestones into spheres he called terrelle, little earths. And to name this second force, he reached back to that Greek word for amber, electron, and coined a new Latin term, electricus. From it came electricity. With one word, a nameless curiosity became a question. What was this invisible pull? Where did it hide inside glass and resin? Could it be summoned at will, or only coaxed out by rubbing? Gilbert had cataloged the mystery, drawn its first map, and given it a name that would outlast his queen, his century, and his own understanding. But he could not produce it in any real quantity. To truly interrogate the force, someone would have to build a machine that made it pour out on demand, spark after spark, whenever a human hand desired. Gilbert had given the force a name, but naming is not summoning. To study electricity, you needed more of it than a rubbed rod of amber could yield. The answer arrived from an unexpected source, the mayor of Magdeburg. Otto von Guericke, the German engineer already famous for pumping the air from two copper hemispheres and daring 16 horses to pull them apart, turned his mind to charge. Around 1663, he cast a ball of sulfur the size of a child's head, mounted it on an iron axle, and set it spinning. As it turned, he pressed his dry hand against the surface. The globe crackled. It glowed faintly in the dark. It attracted feathers, then repelled them, and threw tiny sparks against his knuckles. For the first time, a human being could manufacture electricity on demand, revolution after revolution, as long as the crank turned. Von Guericke had built the first friction machine, an engine for a force no one understood. Others improved it. In London, around 1706, Francis Hawksby, an assistant at the Royal Society working under Isaac Newton himself, replaced the sulfur with a glass sphere. He evacuated some of its air, spun it fast, and rubbed it. The glass didn't just spark. It shone with an eerie purple light, bright enough that Hawksby claimed he could read the letters of a book by its glow. He had, without knowing it, created a crude glowing gas discharge, a distant ancestor of the neon sign. Word spread. By the 1730s and 1740s, these machines had escaped the laboratory and invaded the drawing rooms of Europe. Wealthy salons filled with the smell of ozone and the snap of sparks. Showmen suspended boys from silk cords, charged them, and drew flames from their fingertips and noses. Ladies received tingling kisses that crackled. Electricity had become entertainment, a fashionable, invisible fluid that could be poured into a body and drawn back out. But a spinning globe gives up its charge the instant you stop cranking. The force could be made, yet not kept. Someone still needed a vessel to trap it, to hold lightning still. Every experiment so far shared a hidden assumption. Electricity stayed where you made it. Rub a globe, and the charge clung to its surface, a local glow. Then a retired dyer named Stephen Gray, living on charity in London's Charterhouse Almshouse, discovered that the force could move. In 1729, Gray was experimenting with a glass tube, plugging its ends with corks to keep out dust. He noticed the cork itself attracted feathers, though he had only rubbed the glass. The charge had traveled from glass to cork. Intrigued, he stuck a slender rod into the cork, then an ivory ball on the end, and the ball attracted too. The force ran through the rod. So Gray kept extending the line. He ran packthread from an upper window down to the courtyard. The charge flowed the whole distance. Suspended horizontally on silk loops, his threads carried electricity more than 700 feet. But the choice of support mattered. When Gray hung his line on ordinary hemp cord, the electricity leaked away and vanished. When he hung it on silk, it survived and flowed on. He had stumbled onto the Great Divide. Some materials, metals, water, the human body, let the force pass. These we call conductors. Others, silk, glass, resin, block it. These are insulators. In a famous demonstration, Gray suspended a young boy, face down, from silk cords, charged his feet, and watched brass leaf leap up to the child's electrified hands. Across the channel, the Frenchman Charles Dufay took up the puzzle and found something stranger still. Charging different materials, he noticed they did not all behave alike. Rubbed glass and rubbed amber, brought near the same object, pushed in opposite ways. 2 charged bits of glass repelled each other. 2 bits of resin repelled each other. But glass and resin attracted. Dufay concluded there were 2 distinct kinds of electricity, which he named vitreous and resinous. Like kinds repelled, unlike kinds pulled together. The single mystery had split in 2. Electricity could travel, and it came in opposites. Now if only someone could catch this restless, doubled force and cage it, store a jolt of it to be released at will. The breakthrough came, as breakthroughs often do, by accident, and it nearly killed the man who found it. In the autumn of 1745, in the Prussian town of Camin, a cleric named Ewald Georg von Kleist tried to store electricity in a small medicine bottle. He filled it partway with water, ran a nail through the cork into the liquid, and charged the nail from a friction machine. When he touched the nail to disconnect it, a shock threw his arm back and staggered him. He had trapped charge inside the glass, but his reports were so garbled that few could reproduce the feat. Months later, at the University of Leiden, the Dutch physicist Peter van Musschenbroek stumbled onto the same effect. His assistant, Andreas Cuneus, held a water-filled jar in one hand while charging it, then reached for the wire with the other. The jolt was ferocious. Van Musschenbroek repeated it himself and afterward wrote that he would not take a second shock for the whole kingdom of France. He thought he was going to die, that his body would be torn apart. The device took the city's name, the Leyden jar. It was the first capacitor. A glass jar, coated inside and out with metal foil, with water or shot inside and a brass rod poking through the lid. It could soak up charge from a spinning globe and hold it, silent and patient, for hours. Then, at a touch, release the whole store in a single violent snap. The demonstrations grew theatrical, then reckless. In Paris in 1746, the Abbé Nollet linked 180 royal guards hand to hand and discharged a jar through the entire line. Every soldier leapt into the air at the same instant. He later did the same to 700 monks strung out on iron wire, a human circuit convulsing as one. For the first time, electricity could be bottled, carried, and unleashed on command. A charge stored in glass could deliver a blow like a hammer, and that violent snap looked and sounded like something else entirely, like a tiny bolt of lightning. One man in Philadelphia was about to ask whether it truly was. That man was Benjamin Franklin, printer, postmaster, and self-taught philosopher of Philadelphia. Studying the Leyden jar in the late 1740s, he grew convinced that the tiny spark leaping from its rod and the great bolt splitting the sky were one and the same force, differing only in scale. Both cracked and flashed. Both struck points and sharp edges. Both could kill. If a laboratory spark was lightning in miniature, then lightning was electricity and could be caught. Franklin proposed a test. Stand a tall iron rod on a high tower, insulated, and draw sparks from passing storm clouds. In France in May 1752, following his published plan, Thomas-François Dalibard erected such a rod at Marly-le-Ville and drew crackling sparks from a thundercloud, the first proof that clouds carried charge. Franklin, not yet knowing of the French success, ran his own famous test that June. He flew a silk kite into a Philadelphia storm, a sharp wire at its top, and a brass key tied to the wet string. As the storm passed overhead, loose threads on the twine stood up, and when he brought his knuckle to the key, a spark jumped. The heavens and the jar spoke the same language. Franklin gave that language its grammar. He argued electricity was a single invisible fluid present in all matter. Rubbing did not create it, but moved it. An object with a surplus he called positively charged, one with a deficit negatively charged, the very words we still use. Charge, he insisted, was never made or destroyed, only shifted from one body to another. It was conservation, decades before the idea had a name. And the discovery had teeth. If lightning sought sharp metal points, then a pointed iron rod, fixed atop a building and wired to the ground, could intercept a strike and carry it harmlessly into the earth. The lightning rod, Franklin's own invention, began rising over churches and barns, and buildings that had burned for centuries stood safe. Franklin had reached into the storm and lived, but the sky does not forgive every hand that reaches for it. The next man to try would not walk away. By 1753, Benjamin Franklin's name traveled faster than any ship could carry it. His kite experiment had been repeated in Paris, London, and St. Petersburg, and the Royal Society, which once ignored the American printer, awarded him its Copley Medal. Everywhere, gentlemen raised iron rods into thunderclouds, eager to pull the sky's fire down to their instruments. The lightning rod climbed onto church steeples and powder magazines, and for the first time a violent act of nature seemed to obey a human design. But the storm charged a price for its secrets. On August 6, 1753, in St. Petersburg, the Swedish-born physicist Georg Wilhelm Richmann stood beside his electrical gnomon, an insulated iron rod running from the roof into his laboratory. He wanted to measure the charge of an approaching thunderstorm. As he leaned toward the apparatus, a pale blue ball of fire, perhaps a hand's width across, leapt from the rod to his forehead. The blow killed him instantly. His engraver, standing nearby, was thrown to the floor and the door frame was split. Richmann became the first person recorded to die pursuing electricity as a science, a martyr to the very force Franklin had described. His death proved the point beyond argument. The lightning that shattered oak trees and the tamed spark that crackled from a rubbed glass rod were one and the same power. The heavens, once the domain of gods and omens, were now proven electrical. Yet, for all the triumph, the force remained wild and momentary. Every spark, every jar, every stroke of lightning delivered its charge in a single, violent instant, and then was gone. Franklin's fluid could be summoned, stored, and discharged, but it could not be made to flow, steady and controllable, like water through a channel. Electricity was proven, feared, and famous, but still useless as a working tool. The next breakthrough would not come from a storm cloud or a spinning globe. It would come from a dissecting table in Italy, where a professor of anatomy was about to notice something strange twitching beneath his knife. In Bologna, in the 1780s, the anatomist Luigi Galvani was dissecting frogs in a laboratory crowded with electrical machines. The story, told many times, holds that one afternoon an assistant's scalpel touched the exposed crural nerve of a frog's leg just as a nearby friction generator threw off a spark. The dead leg kicked, violently, as if the animal had come back to life. Galvani, a careful and religious man, could not let the observation rest. For nearly a decade he pursued it, hanging skinned frog legs on brass hooks from the iron railing of his balcony, watching them twitch each time the metals touched. He tried it under thunderstorms and on clear days, indoors and out, until he was convinced the effect did not depend on the weather or the spark at all. The convulsion, he decided, came from within the animal itself. Galvani proposed that living tissue stored its own subtle fluid, animal electricity, secreted by the brain and carried through the nerves to the muscles. The metal, he thought, merely released a charge the frog had held in reserve, like a tiny living Leyden jar. In 1791, he published his conclusions in a treatise on the forces of electricity and muscular motion. The report electrified Europe. Here, it seemed, was the bridge between the physical spark and the mystery of life itself, a force that beat in every heart and flexed in every limb. Physicians imagined curing paralysis. Philosophers glimpsed the secret of the soul. Frog legs became the most famous instruments in science, twitching in salons and lecture halls across the continent. But not everyone was persuaded that the frog was the source. In Pavia, a rival professor of physics read Galvani's paper with mounting skepticism. He repeated the experiments and saw the same kicks, but drew the opposite lesson. To him, the twitching leg was not a battery, but a witness, a delicate detector responding to a current made somewhere else entirely, in the meeting of two different metals. The argument that followed would decide the future of electricity. The skeptic in Pavia was Alessandro Volta, professor of physics and already famous for inventing the electrophorus. At first he admired Galvani's work, but the more he repeated it, the less he believed in animal electricity. The key clue, Volta realized, was the metal. The frog legs twitched most strongly when two different metals, such as copper and zinc, touched the tissue at the same time. When Volta used a single metal, or two pieces of the same kind, the effect faded. The frog, he argued, was not a source of electricity, but a sensitive detector, its moist nerves and muscles simply revealing a current generated where the two metals met. Galvani's living fluid was, in truth, the humble contact of dissimilar metals. The two men fought a bitter public dispute through the 1790s, and to prove his point, Volta needed a source that owed nothing to any animal. He began stacking small discs of zinc and copper, separating each metal pair with cardboard or cloth soaked in brine or dilute acid. Zinc, copper, wet cloth, again and again, a column that grew to dozens of layers. In 1800, he described the result in a letter to the Royal Society of London, the voltaic pile, the first true battery. When he connected a wire to the top and bottom of the stack, it produced not a single fleeting spark, but a steady, continuous current, flowing as long as the chemistry lasted. This was something no Leyden jar or spinning globe had ever done. The pile did not merely store charge and release it in one violent burst. It manufactured electricity, moment after moment, in a reliable stream. Volta could feel it as a persistent tingle on his tongue, taste it as a metallic sharpness, watch it hold. For the first time in history, a human being possessed a source of electricity that behaved like a river rather than a lightning bolt. The mysterious force could at last be made to flow on command, and once electricity could flow steadily, the question changed entirely, no longer what it was, but what it could do. News of the voltaic pile spread across Europe in months, and within weeks scientists were building their own columns of zinc and copper. For the first time, a laboratory could command a current that flowed for hours, and researchers rushed to see what such a force could accomplish. The answer came fastest in London. In 1800, only weeks after Volta's announcement, William Nicholson and Anthony Carlisle ran the current from a pile through water and watched it break the liquid apart, hydrogen bubbling from one wire, oxygen from the other. Electricity had become a tool for taking matter to pieces. No one wielded that tool more boldly than Humphrey Davy at the Royal Institution. Davy built the largest battery yet, hundreds of plates strong, and turned its current on substances no chemist had ever split. In 1807 he passed electricity through molten potash and soda, and out came two shining, furious new metals, potassium and sodium, so reactive they burst into flame on water. Within a year he had isolated calcium, magnesium, barium, and strontium as well. The battery had become a key that unlocked the elements themselves. The pace never slowed. Volta's pile had handed science a steady current, and each experiment revealed a new power hidden inside it. In 1820, in Copenhagen, Hans Christian Ørsted set a compass needle beside a current-carrying wire and saw it swing, proof that electricity and magnetism were bound together. From that single deflection would grow the electric motor, the generator, and the telegraph. In barely 20 years, electricity had traveled from a party trick to a working science, from the crackle of a rubbed rod to a force that split water, forged metals, and moved a needle at a distance. The invisible fluid the Greeks had glimpsed in a piece of amber was now measured, stored, generated, and directed by human hands. Every step had been small and hard-won: an amber riddle, a spark, a stored jar, a bolt from the sky, a twitching frog, a steady pile. Piece by patient piece, the storm had been brought to heel. Electricity was tamed, one spark at a time.